Okay, welcome back. Here we are, we're reviewing the National Electric Code and Electrical Fundamentals. So this is going to be about a 2-hour session, I believe. Maybe we'll try to make it a little bit less than that. So let's get started. There's going to be a little bit of reading on my part. I need you to understand electrical fundamentals, and I'm not quite sure what your exact background is. There are some fundamental questions on the exam as well as calculations. So we're going to go through that, and then I'm going to touch on the National Electric Code, and we'll go from there. So I'm hoping to get this done within the next couple hours. Let's begin. So what's your goal? Goal is to pass the exam. What are you going to do? You're going to pass the exam. Let's talk about electricity. Well, we're going to begin from the atom. What's inside the atom? All matter is made up of atoms. In the center of the atom is a nucleus made up of protons and neutrons. Surrounding the nucleus there is a lot of empty space with tiny particles orbiting the nucleus called electrons. Neutrons have no electrical charge, protons carry a positive charge, and electrons are negatively charged. The positive and negative charges are attracted to each other. The flow of electricity is because of the transfer of these electrons. There's two types of electricity, static electricity and current electricity. Static electricity is when electrical charge electrons build up on the surface of a material due to the transfer of charged particles from one material to the other. It is usually caused by rubbing materials together. The result of a buildup of static electricity is that the objects may be attracted to each other or may even cause a spark to jump from one object to the other. For example, when brushing or combing hair in a very dry atmosphere, the hair tends to stand up and be attracted to the brush or comb. Lightning is one form of static electricity. The basic principle behind lightning is charge separation. This means a pool of positively charged particles, protons, becomes separated from a pool of negatively charged particles, electrons. A charge potential develops when such a separation occurs. Since air is an insulator, meaning it does not conduct the flow of electrons well, the potential required for electricity to move through it is very high. When a discharge does occur between two separate pools of charged particles, lightning occurs. Lightning occurs when enough cloud charging takes place, then a discharge occurs between the cloud and the ground to neutralize some of the charge. Current electricity is different than static electricity. Current is the rate of the flow of electrons. It is produced by moving electrons, and it is measured in amperes. Unlike static electricity, current electricity must flow through a conductor, usually a copper wire. Current electricity is like the current of a river. The river flows from one spot to another, and the speed it moves is the speed of the current. Current electricity is a measurement of the amount of energy transferred over a period of time and is rated in amperes. There are different sources of current electricity, including the chemical reactions taking place in a battery. The most common source is the generator. A simple generator produces electricity when a coil of copper wire turns inside a magnetic field. In an electrical power plant, electromagnets spin inside coils of copper wire, which can generate large quantities of current electricity. There are three major attributes to current electricity: voltage, current, and resistance. Electricity or current flows because there is a difference in electrical pressure or potential between 2 points along a conductor. This potential difference is called voltage. Electrons flow from an area of high potential to a point of lower potential, or voltage, through a continuous circle or circuit. Current is the flow of the electrons, and resistance is what restricts the flow of these electrons. Voltage is the pressure that makes an electrical charge move. Current is the charge's flow at the rate at which the charge moves through the conductor, measured at any particular point along the conductor. The conductor, the wire, metal, etc., offers a certain amount of resistance or restricts this flow, which varies depending upon the conductor's composition and size. Voltage, current, and resistance are all interrelated. You can't change one without changing the other. Current is equal to the voltage divided by the resistance, commonly calculated using the formula known as Ohm's law. I, which represents current, equals V, representing voltage, divided by R, representing resistance. This makes sense because when you increase the pressure of the voltage working on electrical charge or decrease the resistance, more charge or more current will flow. If you decrease pressure, the voltage, or increase resistance, less charge will flow. So here's Ohm's law. Voltage equals I times R. Voltage is pressure. Current is the amount of flow of the electrons through the circuit. And resistance is what restricts the flow or restricts the current. George Simon Ohm was born in Germany on March 16, 1787. Ohm's experimentation with voltage and direct current led him to the fundamental relationship that they are exactly proportional in a perfect conductor. Ohm's law applies to direct current circuits only. Ohm's law is made up of three mathematical equations that show the relationship between electrical voltage, current, and resistance. So again here, voltage is push, the pressure, the potential at the source. Current is the electron flow, and then resistance is what restricts that flow. It's very similar to, let's say, a water hose. At the spigot, at the point where the hose is attached to the spigot, you have pressure. Regardless of whether the spigot is turned off or sealed, you still have a pressure there. And when you open it up, the pressure is released, and then you have a flow of current or water through the hose. And what restricts the hose or the water flow would be the diameter of the hose, which is related to the diameter of the conductor, allowing the current to flow through. So the larger the conductor size, the more current you can have flow through, and that is less resistance to that particular circuit or conductor. Okay, so when a metal wire is connected across the two terminals of a direct current source, such as a battery, the free electrons of the battery and conductor are forced to flow towards the positive and away from the negative terminal. Negative to positive. So electrons flow from the negative terminal of the battery to the positive terminal of the battery. We can imagine particles with negative electric charge flowing in this direction around the circuit, like the blue dots in this diagram. This is the real direction for the flow of electrons in a circuit and is referred to as electronic current. There are two main kinds of electronic current: direct current, DC, and alternating current. It's easy to remember. Direct current is like the energy you get from a battery flowing only in one direction. Alternating current, however, is like the power receptacles in the wall, which flows alternately from negative to positive, reversing the directions of the current flow back and forth in the electrical conductor. The difference between the direct current and AC current flow is that DC is a flow of energy in one direction, while AC turns on and off, reversing the direction of flow of the electrons. Direct current flowing through a conductor produces a small electromagnetic field around the conductor. However, alternating current produces an intense electromagnetic field around the conductor it is flowing through. This electromagnetic field can produce interference in other conductors and electronics transmissions and systems, and is referred to as electromagnetic interference, EMI. If high voltage AC wires and low voltage wires have to cross to reduce the effects of EMI, cross them at a 90-degree angle. So this has been an exam question before. If you're running a low voltage communication circuit through a ceiling roof or drop ceiling tile area, and you're going to cross it over a, say, power conductor, you want to cross that at a 90-degree angle so there's less point of intersection. If you run it parallel, there's more EMI, or electromagnetic interference, or flux that can get into that particular conductor and cause it problems, the signaling problems. Here's an example of a direct voltage sine wave. You can see where you have the blue line represents the solid state, flow of a direct current, and then you have the AC sine wave, which goes positive, negative, positive, negative. And this occurs in the United States at 60 hertz, 60 times a second, 60 cycles. In Europe, it's 50 cycles, and in the United States, it is 60 cycles, 60 times a second. Let's talk a little bit about transformers. Not really these types of transformers, but these types of transformers. Our low voltage systems work on class 2 transformers, and this is a very typical for alarm systems, telecommunication systems, fire alarm systems, and other types of low voltage systems. They work from class 2 transformers, which are connected to class 2 circuits, and those circuits basically are rated for reduced, fire load. So here's an example of a transistor or a transformer, and you have a coil on one side and a coil on the other side, and you have alternating current flowing through that coil and inducing a magnetic field effect which transfers the electrons from one side to the other. So most transformers with iron cores can be considered an ideal. When you use them, an ideal transformer has no losses. So the energy transfer from the primary circuit to the secondary circuit is perfect. What you need to know for the exam regarding transformers is that you have a primary side, and for a step-down transformer, the primary side would have more wraps or more turns, and the secondary side would have less turns. So if you had a situation where you had 100 turns on the primary side, it was 120 volts, and it was a step-down transformer like in this example here, and you had 10 turns on the opposite side, you would reduce the voltage by a factor to 12 volts. Okay? So the less turns you have on the opposite side of the secondary side would cause the voltage to drop. All right. If you have the opposite effect, if you have more turns on the secondary side, then you would have the voltage increase, and that would be considered a ballast, like what they use for fluorescent tubing. Here's a schematic representation of a transformer. There are some symbols on the exam that you would need to know, and this might be one of those. Shows that your input side is 120 volts. This is a very typical class 2 type transformer. You have your step down on the opposite side of 12 volts. So remember this if you can. Primary side 120 volts, you got 100 wraps, and it's reduced to 12 volts on the secondary side, step down, and you would have how many wraps on the secondary side? You would have 10. Okay. Here's a schematic diagram of a AC to DC circuit. We, as low voltage contractors, we need smooth direct current voltage sources in order to work with our switching services, systems, and so forth. So how we do that is we take a input from a class 2 type transformer that is a alternating current transformer that's plugged into a receptacle. You take 120 volts from the primary side down to the secondary side, which would be less coils, and you would drop the voltage to whatever you had desired. Let's say it's 12 volts. So then you've got alternating current here coming through the transformer, as you see at the top of this schematic diagram here, the little blue sine wave there. And then it goes into a series of diodes, because we have to take that alternating current, we have to change that into direct current. So it goes through a series of diodes called a bridge rectifier, allowing the electrons to only flow in one direction. And then you can see you have a capacitor there that represents a capacitor there with that little C by it, designating it's a capacitor. And that capacitor will charge up on the high side, and then on the low side it'll discharge, and it'll give you a smooth output of direct current, which you can use to charge batteries and run our switching systems. Okay. There's two types of electric circuits that we need to be concerned about, one being series, the other being parallel. And basically, an electric circuit is a combination of metal conductors and equipment that can include things such as switches and electric lights. These circuits can be connected in two ways, either in series or parallel. In a series circuit, the electrons or the current has one circuit or one path to flow through, one travel path. You can see in this representation here, you have a green battery source, power source, red wire running through two lights, and there's only one path for the current to flow through. Series circuits have the same current flowing through each part of a series circuit. So if you look at the schematic representation here, you can see resistor 1, 2, and 3. They all have the same current flowing through those resistors. The voltage, however, applied to a series circuit is equal to the sum of the individual voltage drops. So basically, R1, R2, and R3 resistors there have different voltage, or have a voltage based on a combined voltage at the source. Okay. Now we don't need to know that about voltage drop along a series circuit, because there's really nothing we deal with that shows voltage drop along a series type of circuit. The voltage drop across a resistor in a series circuit is directly proportional to the size of the resistor. If the current is broken at any point, no current will flow. So in a series circuit, if you break the wire or the circuit along any point, it'll end the flow of the current. This is a schematic representation of a series circuit. You show your power supply on the left. That's a schematic representation of a power supply. And then you've got your resistor 1, resistor 2, and resistor 3. Those are examples, a schematic example of resistors. And that's something you should make notes of, that more likely will be on your exam. Then this is a closed series circuit because it's got a complete flow through it. This is a open series circuit because you've got a switch in the loop. C1 is contact 1, it shows open. C2 is contact 2, it shows open. L1 is a light bulb. So C1 would have to be closed, which is a switch, and then C2 is a momentary push button. That would have to be closed in order for L1 to light. Parallel circuits. A parallel circuit gives electricity a choice of paths to flow along. Buildings are all wired in parallel circuits. Okay? A parallel circuit, as you can see from this representation here, of this green being the power supply, the battery, when you go to the first light bulb, you go to the first light bulb from one side of the source, and then you go to the second light bulb. So if the wire was broken between the first light bulb and the second light bulb, the first light bulb would still be lit if it was powered. So a parallel circuit, what you have to remember about that is that there's more than one path to flow along. Okay, more than one path. When you follow the power out from the source, if it goes to two places, all right, along the path, they're in parallel with each other instead of series. So you need to understand that a parallel circuit is has more than one path to flow along. Now, what is wired in a parallel circuit? Well, fire alarms, smoke detectors, heat detectors, manual pull stations are all wired in parallel circuits. What's wired in a series circuit? Well, alarm contacts are wired in series circuits. So if one alarm contact opens the circuit, the whole circuit opens up. So series circuits are used in low voltage systems, and parallel circuits are used in low voltage systems. This is an example of a resistor. I showed you the schematic representation a little while ago of a resistor. Pretty much need to just know that there's different sizes of resistors, and the fact that they look like a representation of a zigzag line. There it is. And they're represented by the symbol ohms. Okay, ohms represents resistance. You can see in this circuit type here, the little, I call it upside down horseshoe, is basically what the symbol is for the ohms symbol, meaning resistance. You need to know that. That is what we're looking at there. That is a parallel circuit. Okay, because why? Because there's two paths to flow along. Because you've got your battery symbol on the left, you come out of the battery and you go to the first resistor, but it splits there. It has two paths there that are in parallel to each other, meaning right next to each other. So your first resistor gets a flow of electrons and your second resistor gets a flow of electrons. They meet and they come back to the source. That's a parallel circuit. And that's a closed parallel circuit. Okay? So the parallel circuit has extremely different characteristics than a series circuit. For one, the total resistance of a parallel circuit is not equal to the sum of the resistors like in a series circuit. Now in a series circuit, to figure out the total resistance, all you need to do is add up all the resistors along the path, okay? So resistor 1, 2, 3, 4, 5, etc. You just add them all together, and that gives you the total resistance of that circuit. However, in a parallel circuit, it's different. The total resistance in a parallel circuit is always less than any of the branch resistances. So, you know, if you've got 3 resistors in a parallel circuit, and you've got one that's 1 ohm, 2 ohm, 3 ohms, you know that the resistance of that circuit, measured from the power source, is going to be at least less than the 1 ohms. Okay, and a lot of times you can answer the question. They ask you about parallel circuits and what the resistance is. You can answer that by looking at the parallel circuit and looking at the resistor and looking at the least resistance of the circuit, of the resistor of that circuit that's in parallel, and you can say, you can find the answer because it would have to be under that least resistor. Okay, it's never going to be above the lowest resistor of that particular circuit in parallel. So in this example that's on the screen here, we're looking at we know the resistance is at least what? K represents 1,000, so 3 zeros. So the first one, R1, is 10,000, R2 is 2,000, R3 is 1,000. I can tell you just by looking at that without even calculating that the resistance of that circuit is going to be less than 1K or 1,000 ohms, okay? The more branches you add to a circuit on a parallel circuit, the less the resistance. So as you continue to add resistors on a parallel circuit, the resistance gets less. Now, why is that? Let me just give you a representation of so you understand that. Let's say if you've got, let's take a look, example, back to the water hose. The water hose is on the spigot, you got the spigot open full, you got the hose going out, and it's got a sprinkler head at the end, okay? Well, that sprinkler head is holding back that water, you know, because based on the opening of the sprinkler head and so forth, it's holding back some of that water. If you add another sprinkler head onto that, into that same path, and then you add another one and another one, each time you add a new sprinkler head, the pressure will get less and less. So eventually, if you added a lot of sprinkler heads, the water would just be trickling out of each of the heads, okay? So that's the same situation with the current flowing through the resistors. The fact that when you have more branch circuits, when you have more resistors, you have more current flow and you have less resistance. The reason you have more current flow is because you have less resistance, because you have more resistors in the circuit. All right, and that gives them more paths to flow along. So the current has more places to flow along. All right. This is all basic circuitry that you should have a grasp on if you've been working in the field. A parallel circuit has 2 or more paths of current to flow through. Voltage is the same across each component of a parallel circuit. So the voltage remains constant across resistor 1, 2, and 3. It's the current that divides itself out amongst the circuit. Now, you don't need to know that for this exam, other than the fact that a parallel circuit has more than one branch that it flows along. So basically, remember the fact that on a series circuit, you only got one circuit flow, one path, one wire that goes around and comes back to the source. It goes, whatever the power supply is, it goes out and it comes back. And then you have, on a parallel, when the power goes out from the source, it splits. So it goes to more than one source, more than one load, like, let's say. And we're using the resistors here as an example of a load. It could be any kind of load, a motor, a light, any kind of load, okay? But a resistor would be considered a load as well. So this is a combination circuit. It's called a series parallel. And look at this closely, because many times students don't understand this. They look at this and they say it's a parallel circuit. But in reality, look at it closely. R1 and R2 are in parallel with each other. Okay? And R3 and R4 are in parallel with each other. That is true. But the combination of R1 and R2, okay, and the combination of R3 and R4 are in series with each other. Okay? So R1 plus R2 makes up one resistance loop, and then R3 plus R4 makes up another resistance loop, right, or another resistor. So you got two resistors, and those two resistors are in series because there's only one path to flow along when you add those together or combine those together. Little confusing there. There is an example of this on the exam that I gave you, and that is the one that has been on the test forever. So when you see that and you look at the answer, it'll say that it's a series parallel. There is no parallel series, it's always series parallel. But the thing is, on the exams I've given you, make note of that. If you get that wrong, just realize that is a parallel circuit. I may have it on this overhead, I'm not sure. We'll have to keep going and see, okay? What is an insulator? An insulator is anything that restricts the flow of the electrons or the current, okay? Electrical tape is an insulator, okay, too. Everything can be broken down, but, and you know, it can be actually arced based on the pressure, the voltage, right? The higher the voltage, you know, causes, it will push those electrons through even any insulator. But basically, electrical tape is used in an insulator. One of the exam questions has always been, when you cover up, when you put wires together, how many wraps do you need to go around the conductors? Like say if you put on a, you twist two wires together and then put some kind of a wire nut on them or a connector. So you want to wrap them twice, okay, 2 times around. And also in the UL it says if you go over a sharp corner and you're pulling wire, you want to cover that sharp corner with 2 pieces of electrical tape. And that's been on the exam before. It's kind of silly, but I guess that's so you don't cut the wire or something, but it's 2 pieces of electrical tape over the edge of a sharp corner, okay? You'll see that in the UL 681 book, but silly question, has been on the exam before. Now you know the answer, and hopefully you'll just remember that. Okay, this is an example of resistors. And again, it's that zigzaggy line there. That's the schematic representation of a resistor. So if you see that on your exam, that's a resistor. Now that's just some kind of a device. That one that's showing there off to the right, that one is a, it's basically, it could be a wire, a round resistor, there's wire in there, or it could be a carbon resistor of some sort. The stripes on there indicate the amount of resistance, and I'm going to show you that briefly. You won't need to know that, as far as I know, at least on the Georgia exam. I haven't heard anything about that, but I'm going to show you real quickly how you do that. Those stripes do mean you basically, the color determines the amount of resistance in that particular resistor. Okay, and all they do, all a resistor does, and remember, it restricts the flow of electricity or current or electrons. They're all the same. Electricity, current, electrons, flow, I mean, that's all the same thing we're talking about here. Those are all synonyms of each other. You know, to some degree. I mean, not exactly the same, but electron is an electron, and current is, you know, a representation of many electrons flowing through a circuit. But still, they're basically the same thing. Okay, it's just the same thing as conductor and wire. You know, that's the same thing. I mean, a wire is, you know, but you could have a wire and it not be a conductor, of course, but or a cable could be considered a wire or conductor too. So you have to be looking at the available choices, and you have to realize that they're not maybe going to exactly match what you have found in a reference book or something like that. But you have to take the closest choice to that. So if somebody says a wire, and you find circuit or you find conductor in the code book, and it's referring to a conductor or a circuit, well, if they have something in the answer, the only best answer is wire compared to like say insulator or dielectric or something like that, or inductor, the wire would be the only choice that would be close enough to what it actually was listed in the code book. So keep that in mind. You know, this is not a perfect science here when it comes to them writing these questions, and you have to just kind of give them the benefit of the doubt, and you have to pick the best choice available that closely matches what you're seeing as the reference in the code book. Now, most of the time it does match exactly. I mean, most of the time you can actually go to a question and you find the exact text in the code book, which is kind of cool. I mean, it's nice because, hey, that's it for sure. I mean, there it's written exactly like it is in the answer, or in the question even sometimes. So just keep that in mind, though. I don't want you to get so focused on, well, it has to say this or it has to say that. No, no, no. If it says it's the owner in the code book that has to keep the instruction books or the manuals, for example, and you find that the answer or the best choice is the, it's not the owner, is not listed, you find the best choice is the manager, then it's the manager, okay? So just keep that in mind as you go through this as well. Okay. So this is a schematic representation of a fire alarm system, smoke detectors. You have your power source being A there. That is a typical example of a schematic for a power supply. Now that could be a battery. It could be a DC power supply of some sort. It's a DC power supply. The reason I know that is because it's got smaller lines in between there. But in any case, regardless of that, you need to know that symbol. That symbol is a power supply symbol or battery, whatever is that's another synonym there. That could represent a battery or it could represent a power supply. Okay, but if you're looking up something and the only choice there is power supply, but to you remember battery, that's the same thing. A battery is a power supply, right? It's supplying current and power to voltage and so forth to the circuit. So in this representation here, you have a power supply and you have a smoke detector. That's a circle with that little backward S there, little snake there. That's a smoke detector. Now this stuff is common knowledge stuff, but some of it's in the books. In the National Electric Code, you have the symbol for a ground, which is number D there, but they show it with a circle around it. I call it an upside down Christmas tree, but in the NEC in Article 250, that is shown as a symbol there with a circle around it. Now, if the answer didn't show the circle around it, well, that's okay. If that's your best choice, there would be that upside down, Christmas tree or whatever you're going to call it. So the other representation there, B, is those are smoke detectors. And then the EOL, that is what? That's a resistor. But that's a very common acronym for end of line. And what do you have at the end of line in burglar and fire alarm circuits, especially fire alarm circuits? End of line resistors. Now, I'm not going to get into this in any detail, but an end of line resistor is used on the end of fire alarm circuits for supervision of the circuit. And so that the wire, if it's cut, then they know, the panel knows that it's been cut, and then it can send out maybe a trouble signal or something, or some kind of audible signal, enunciating that, there's a trouble condition on the circuit for whatever reason. So that has been on the exam before. That circuit there with that resistor at the end of the line, that's called the EOL, end of line resistor. Now again, these questions and this stuff I'm going over now is just giving you some visualization of and these have all been on my exams before. So I'm sure you've seen these representations on the tests for fire alarms, okay? And again, you just want to remember this, and I just want to give you some visualization of this. Okay, these are variable resistors. Now, what I've seen on the exam before is, see the resistor on the left side there showing the resistor, and then it shows like an arrow through it. That arrow through there means variable. Okay, that means that you can actually turn it or adjust it. You can turn those ones down. Those are also called potentiometers or rheostats. You may have heard those before. But you can turn a knob or a dial, or even with those are like set screws there, and you can turn it and make the resistance more or make the resistance less. Okay, and that the variable part of that is the arrow. Now, this I have not heard that's been on the exam. What I've heard is on the exam is a capacitor, a variable capacitor. I have no idea why that ever is on the exam, because there's no representation in any book about a variable capacitor. But if you remember, I showed you the capacitor before, which was a couple, almost looks like a contact, and I'll show you that later, but just two plates with the wires coming out here and out of here, and then you have the arrow through it. So that's a variable capacitor. Okay, if you don't know what I'm talking about or what that reference, you just look it up on Google and you go variable capacitor schematic diagram, and just they'll see it there under images. So this is variable resistor, and I don't believe this has been on the exam before, but I wanted to point out what it was in case it was, and also the variable part of it, which is the arrow. Variable capacitor has been on there, and again, I don't know where they're getting that symbol from, because it's not on anything. And frankly, in the low voltage trade, there's not any time we use a variable capacitor. I mean, the only variable capacitor, I mean, I don't know when we ever use one. We do use variable resistors sometimes. That's a possibility, but not variable capacitors, but they've had that on the exam before. So maybe it's one of those dummy questions. Okay, going forward here, this is the ohms meter. Some kind of a question like this, and basically it's asking you what type of meter you need to use to measure the resistor in this circuit, and you measure resistance with ohms. Okay, ohms. Resistance is measured in ohms. Remember George Simon Ohm? I mentioned him earlier. Well, okay, that's it. And that's that little upside down horseshoe, whatever you want to call it there. It's better represented on this overhead here, right down there. I can't reach over there. But in any case, you can use a ohms meter or a multimeter. And what a multimeter is, it just has multiple functions. Ohms, voltage, current can be measured on a multimeter, but it's basically measured with ohms meter. Okay. Now, on a series and parallel circuit, let's get back to this. These are the actual formulas. And I'm not going to go into too much detail on these, but I want you to look at them. If you need any additional help on those, you can email me and I can give you some references on them that will probably help you out so you understand them. They're really pretty simple though. For a series circuit, remember it only has one path to flow along. You just add up all the resistors. That's it. So whatever the number of resistors are along the path, you just add them up, and that gives you the total resistance of the circuit. Really easy. On a parallel circuit, a little more complicated. I'm going to show you a real quick shortcut here, and they don't make them difficult on the exam. Actually, they're pretty easy, and I've got them on here, so I'll show you what they are. Okay, let's look at this image here. You've got, whenever you measure resistance, you measure it without the power in the circuit, because that would cause a problem. You got to remove all the power. So, you got to have to kind of visually look at what you're doing here. So let's say, what is the resistance between point A and B here? All right. So between point A and B, it's a series circuit. I'm simply going to do what? There's three resistors there. One's 3 ohms, the other one's 4 ohms, and you have 12 ohms. You add them all together, and what do you come up with? Well, there's your formula. R total equals R1 plus, R1, R2, R3. Series circuit. And you come up with what? You can do that with your hands. And this is going to show you a breakdown of what we're doing here. So it's 3 plus 12 plus 4, you come up with 19, and it's measured in ohms. Again, upside down horseshoe next to it, 19 ohms, OHMS, George Simon ohms. Okay, so now here's a parallel circuit. How do I know it's a parallel circuit? Well, let's say I usually go, myself personally, I usually trace out circuits by going from the negative forward, but you can trace out a circuit by positive or negative side of the power supply. It doesn't really matter. So let's just say we're going from A. So as my little electrons flow along that circuit A, as it goes out, it hits that junction there, and it goes down to 1/8 ohms, and then it goes, the other part of it goes to the other 8 ohms. So that means there's more than one path. There's actually two paths along the circuit there, okay? One is to the first 8 ohms, and the next is to the second 8 ohms. If you know anything about speakers, when you parallel speakers, speakers come in 8 ohms. I mean, each speaker is 8 ohms. And if you put two speakers together, and they were equal resistance, and they were both 8 ohms, basically how you figure out the resistance of that circuit is you just take the fact that there's two resistors or there's two paths, and you divide that into the resistor value of the resistor, which in this case you've got two paths or two resistors, and you divide 2 into 8. So the answer here for the resistance between point A and B would be 4 ohms. And this is the one that has been on the exam before. You can do it by this actual formula here at the bottom, where it's R total. Let me take you back there. Here it is. R total equals 1 over R1 plus all that. So if you take that out, this is what you're going to get. Okay, so it's 1 over 1/8 plus 1/8. So you figure the math on that, you get 0.125 plus 0.125, and you get that by taking 1 and dividing 8 into it. 1 divided by 8, okay? 0.125 plus 0.125. And you've got to do that actual calculation. And then you divide that total, 0.25, into 1. So it's like $1 divided by a quarter, right? Goes in there 4 times, okay? So the answer would be 4 ohms here. But the shortcut I showed you, you know, in that, really they don't have them any more complicated than that. But the shortcut I showed you is you just know that there's 2 resistors in a parallel circuit, or maybe 3 resistors, whatever it is. And so it's 2 resistors in this one. You take 2, and this only works if the resistors are the same value. If they're different values, this shortcut doesn't work. So you got 2 here, and 2 divided by 8 is 4. See, and that's how you get it. So here's one. It's different. It's 4 ohms and 8 ohms. So you got a little different circuit here. It's still a parallel circuit. You got 2 branches or two paths to flow along, or 2 resistors there in parallel. And one's 4 ohms and one that's 8 ohms. What do I know about this circuit? I can tell you right away that I know what the value is less than. Remember earlier I said if you have a parallel circuit, it's always the resistance, the total resistance of the circuit is always less than the smallest resistor value. So I know it's under 4 ohms, okay, because it's a parallel circuit. There's more than one path to flow along, it's parallel, so I know it's under 4 ohms. Now maybe I don't even have to do a calculation, and a lot of times that's the case. Maybe the answer would be like, 3 point something, and then 6, and then 8, and then 12, right? Well, I don't even need to calculate that because I know it's under the 4 ohms, right? And the only one on the choices available is 3.6. Now, I don't know if that's the answer, but I'm saying that's one way of doing it without even having to do a calculation if there wasn't any more than one choice under 4 ohms. You follow me on that? Okay. But let's go calculate this out as we would with the actual formula. Now, one thing I want to mention is formulas. Where do you get these formulas? Well, you suppose I guess actually remember them, but I've given you these actual formulas inside your electrical safety plastic packet here. So inside here, you'll see I provided you with some supplementary information, and one of those things is here that you've got your formulas right here, okay, for your, I'm not sure how that's showing up there, but in any case, you can look at that sheet. It's parallel and series circuit formulas. It also gives you your ohms wheel here and several other items that are important that have been on this exam. So you want to take those, and I would put those into your employee's tax guide, okay, this book here, or one that you've made up for that. And you've got stickers here that go for those that help you there, okay? They say conduit fill, Ohm's law, parallel and series circuits. You can stick those on those papers so that you can find them easily if you need to get to them, okay? That's important because you're not going to get those formulas anywhere else. They don't have them in the books, unfortunately, and they do ask, on some of the categories, they do ask questions on the exam. And in fact, they ask these questions on the general exam as well. So even if you're a general individual here, those are kind of questions you would still get. This is basically fundamental electricity, electronics. I mean, it's something you should know if you've had a year of experience in the trade. Well, they say you should know it. I'm not quite sure you should know this, if you haven't certainly worked with this. A lot of people don't. They just look at the manuals and stuff, and they don't really understand the underlying, relationship in between electricity and electronics. So this is kind of giving you a brief and very fast. I know I'm talking fast. A very brief and fast tutorial about basic electricity and electronics. So. If there's anything here I'm saying, I'm talking very fast. If there's anything I'm saying you're not keeping up with, or you don't really have a good understanding of it, drop me an email, and I'll give you some links to some other places that have got a lot more detail, or I'll talk to you on the phone about it, and we'll get it worked out to where you understand it before you go take the test. Okay. So here we go. We do the calculation now. Remember, in this circuit, it's a branch, two branches here. So you've got a parallel circuit. So basically, the formula is R total equals 1 over 4 plus 1 over 8. Now, you can't just add those together at the bottom. You've got to calculate them out and then add them together. So be careful with that. You want to make sure you calculate them out. So it's 1 divided by 4 plus 1 divided by 8. So 1 divided by 4 is 0.25. You should maybe do that on your calculator as we go through it. And 1 divided by 8 is 0.125. Now, again, I don't know of any, they've all, from what I've heard and seen or whatever, they've all been equal values. And of course, if you do that, they're equal, they're easy, you just divide them by the number of resistors and divide that into the value of the resistor, So if it's not equal, you got to do the formula. So that means 0.25 plus 0.125, you come up with 0.375. Now you got to divide that into 1. So it's 1 divided by 0.375. Don't make the mistake and do it the reverse. And that's 2.6, okay? So again, that is less than 4, right? 2.6? It's less than 4. Remember I said that would be less than 4? So 2.6. Now, if it's above 0.5, in any kind of a notation, whether it be a fraction of some sort or what, if it's above 0.5, you can round it up. So don't be spooked if you come up with an answer of 2.6 and all you see on the exam is 3, okay? Because they just rounded it up. So anything 0.5 and above, you can round up. Anything under 0.5, you can round down. You follow me? So if that was 2.4, you could round it down. Now, you don't round it down normally because the answer might be 2.6. So you only look at the available choices, and if the available choices doesn't have a 2.6 and it's got a 2 and it's got a 3 as available choice, which one are you going to choose? Well, you're obviously going to round up because it's 2.6 to 3. Now, if that was 2.4 and you had a choice of 2 and 3, you would round it down and you would choose 2. Okay? This is just common mathematical, stuff, the rounding. So just keep that in mind because sometimes the exam doesn't have the specific answer. They've rounded it. And sometimes that, confuses people. I don't see the answer available. And it just remember, because it's important, because if it was 2.6 and you saw 2 and 3 as choices, right? And you said, well, it's, you need to know that it's closer to 3 than it is to 2. Because 0.6 is closer to 3 than it is to 2, right? Okay. I'm sure you understand that. Let's hope, huh? What is the resistance between point A and B? Okay, now this is one I give to the students during my workshop, and I actually give them like 15 minutes to figure it out. And actually, some people have trouble with this. I mean, quite a few actually. You've got 2,400 ohms, 400 ohms, and 800 ohms. First of all, what type of circuit is this? Take a close look at it. And first you got to say to yourself, is this series or is it parallel, right? So, okay, I'm looking at this circuit. Well, it's got more than one branch, right? Or more than one resistor that's next to each other in parallel, right? So what does that mean? When you go, well, let's take A, and let's say we're running our current through A, and if we come to 2400 resistor, right? Some of our little electrons go that way, and then we've got the other ones going down the path further, and then they go off to 400 ohm resistor, so some of them go that way, and the other ones go down to the 800. So you're splitting all those little electrons, and that means there's more than one path, right? So you can see that. So you're going, yeah, just like you're on a trail. You're walking down a trail. There's another path off that trail, right? Then you go a little further down. There's another path off that trail. That's what we talk about when we talk about paths. It's paths, flow of the current or the electrons through the circuit, and it has more than one place to go to. So tells me right there then that is what? That's a parallel circuit, right? So okay, so we know it's a parallel circuit. So what formula are we going to use? Since they're not all the same, if they're all the same, we could just divide it by the number of paths, right, or number of resistors, but they're different, so we got to use this formula. Now again, the only place you're going to find this formula is going to be right here, okay, on that sheet. Again, I don't think you're going to have anything like this, but it's important that you understand it, because if you do have something like it, then you're not going to get it wrong if you understand it. So basically, you got this formula: R total equals 1 divided by 1 over R1 plus, R2 and R3. You come up with, well, okay, here's the answer: 240 ohms. And I apparently haven't worked it out. So this because I have this on the workshop, and we all talk about it. But in any case, you should figure it out. I take that example there. Okay, 2400 ohms, 400 ohms, 800 ohms. Stop the video if you and try to figure it out. Try to make sure you get 240 ohms. Okay, if you don't, you have problems with it, give me a call or drop me an email, and we'll work on it together. Okay, because I'm sure it's simple once you really understand it. This has been on the exam. I mentioned earlier about the series parallel. Okay, and also the series and parallel circuits. Now this is one right off the exam. Okay, so you look at this, and it says, what is the resistance between point A to B in the following circuit? First of all, notice all the resistors are what? 12 ohms. They're all the same, right? Okay, but forget about that. Now, many people say to me right away, this is a series parallel circuit. Okay, nobody really says it's a series circuit. But the reality of this is not a series parallel circuit. This is not a series circuit. This is a parallel circuit. And this is the way they draw it. And again, they're trying to confuse you. Well, they're actually trying to see if you have an understanding of circuits. Because if you look at this and say this is series parallel, you don't understand what's going on here. And let me try to explain it to you. And believe me, if you don't understand this, you're not alone. Half the class normally says this is a series parallel circuit, especially after the fact they just got done talking with it, and they glance at it and they say series parallel, and they don't give it a second thought. And you got to be careful about that. Just because they draw it this way doesn't mean that it is series parallel. Let's take the way that I would look at this. You got, what do you have on the very left-hand side there? You have the source of power, right? That little symbol there, that little lines drawn there. That's a power supply of some sort, right? A battery or something. So why don't we do this? From the battery source, you take and look at it, and the electricity flows from one side of the battery. Doesn't matter which side. And let's just take the top side. Say it flows out the top side. You can do this with both sides. It doesn't matter. And the electricity flows up, that goes to the right, and then it goes over to point A, right? Okay. Now what happens at point A? At point A, it goes down, and it splits and goes to the right, goes down to that 12 ohm, then it goes to the next 12. So what's happening there, it's basically point A is feeding what? All sides of the 12 ohm resistor. And so is point B feeding the other sides of the 12 ohm resistor. So they just put lines in there to kind of confuse you. It doesn't matter that there's a couple extra lines in there, or wires in there. They all go back to point A regardless. So there is how many paths there? There's 4 paths there, okay? So they're not in series at all. They're all in parallel. The 12 ohms is in parallel with each other. Since they're all equal 12 ohms and you're in parallel, and I have 4 paths or 4 resistors, either way you want to think about it, I just got to divide, shortcut, 4 into 12, and what do I get? 3. Okay? It's as simple as that. Now this is on the exam, and more likely it'll be on your exam. Maybe not. I mean, this is one that comes up all the time. So if you don't understand that, just remember it's 3. Okay? It's D3. It might not be D3 actually. I don't know where the answer is, but it is definitely 3. And if you went to the formula that you have on the sheet of paper here that I've given you, you can actually figure it all out and put them all in there. 1 over 12 plus 1 over 12 plus 1 over 12 plus 1 over 12, and divide that all into 1, then divide it into 1 again, and you'll come up with 3. All right? But the key here, number 1, try to remember this. And I'm hoping you see it and you say, oh, that's that one Steve was talking about. Hopefully you remember that it's not a series parallel circuit. It is a parallel circuit, and what do you do in that case? Since all the resistors are the same, I've given you a little shortcut. You don't even need to use the formula. Basically, you got 4 12 ohm resistors in parallel, so that's 4 divided into 12, and you come up with 3. Okay? It's that simple. But if you don't understand it, give me a call, or better yet, drop me an email. I'll send you some information, and then we can talk over the phone. Okay? All right. Okay, now let's go into Ohm's law. All right. Now there is some questions regarding Ohm's law, and I'm going to try to explain this to you as quickly as possible. It's actually relatively simple. You have 2 ways of, and I've given you these, by the way, on this part of the form. You have your triangle and your actual wheel here. 2 ways of using it to figure it out. Now, obviously, I'm just starting to use this this program here for broadcasting this stuff, so I don't really know how I can write or put a pen up there to show you some things. So I'm going to have to try to visually or describe it visually as the best I can. So there's 2 ways of doing this if you're figuring out anything. First of all, on the left, you see that you've got this thing called Ohm's wheel, okay? And basically that symbol at the top is the ohms symbol, right? That means resistance, right? So, and you're, when it comes to figuring out, all circuits have voltage, right? Voltage, and they also have current flowing through them, and they also have resistance that restricts the current or restricts the flow, right? Voltage is the pressure, the potential, the push, and then you have, current. Let me kind of explain something to you here, and maybe this will make sense to you. Let's take a 12-volt car battery, right? Now, a 12-volt battery is a big battery, right? I mean, it's a big battery. And, if you take a screwdriver and you put it across those 2 terminals, I'm not sure if you've ever experienced anything like that, but let me tell you, there'd be a big spark, and that screwdriver would get hot real fast, okay, would glow. But if you take your fingers, and even if you lick them and put them on the battery and you're soaking wet, you won't get shocked at all. Nothing will happen. Why is that? Well, because that's got a lot of current in that battery, But the thing is, it's only got 12 volts. It's only got a little bit of push, okay? A little bit of push. So your wet fingers and soaking wet body, no matter how wet you are, your fingers on those 2 terminals are not going to be, there's too much resistance in you that 12 volts cannot push that current through you. But if you put a screwdriver across there, there's not that much resistance on a metal screwdriver, and all those amperes, all that current, all that flow will go through that screwdriver very fast, and it'll heat up very fast. It needs that current to push that motor, to start that motor, but it doesn't need a lot of push, okay? That's why you don't get shocked on a 12-volt battery, because there's no push behind it. Now, on a receptacle, you got 120 volts of push, right? And even if you had low current, you could still get shocked because you've got a lot of push there, and it can push that current through you and you can feel it. That's why those little taser guns and everything, you're talking about, they can take a 9-volt battery. I've got one, and it puts out like a million something volts. Take a 9-volt battery, and they can shock the heck out of you, right? Because they take that 9-volt battery and they put it through a transformer, but it's a ballast type transformer. It takes it and they pulse it through there, so it puts out its magnetic field. And what happens is it picks it up on the other side, and there's a lot more wiring on the other side, coils on the other side, so it increases the voltage. And the voltage is the pressure, right? So when you get hit with that pressure, it doesn't matter if there's not much current in that little 9-volt battery, but that voltage pushes that little bit of current through you, and it shocks you silly, right? Okay, so that's the difference. I mean, that's how fluorescent lights work. You know, you have a black ballast in there. I don't know what color it is, but it's usually black. And what that is, that's your reverse transformer. That what you have is you have the smaller windings on one side and a lot of windings on the other side. And when that little magnetic field goes into those bigger windings, it makes more voltage or increases the voltage, okay? And what happens is you need high voltage to arc through the gases in the fluorescent tube. You need a lot of potential or push there to push that electricity, that current, through that tube. And you got, it fluoresces based on what chemicals are in there, gives you the different colors and different temperatures of light and stuff like that. So that's what those are. Those ballasts, they're just reverse transformers. So there's 3 functions of a circuit. You have your voltage, your pressure, your push, your potential, your current, which is well, they call it current, kind of like a river current, current flowing. And then you also have your resistor, your resistance of the circuit. Even wire has resistance. It has some kind of restricts the flow. I mean, even the copper is some kind of resistance, And the smaller the conductor size, the diameter, the more resistance there is, because the little electrons get bumping into each other and they get hot, and you have to have a bigger wire to get more electrons, more current down there. So in Ohm's law, he discovered that there's a proportional reality to voltage, current, resistance. When you change one, it affects the other. Okay, so when he come up with this formula that works. Like, for example, if you look at the Ohm's wheel here and you look into the center of the Ohm's wheel, see where it says watt, amps, volts, and resistance. That's when you could always measure the circuit with a multimeter, a voltage meter, a current meter, or an ohms meter, right, resistance meter. But if you're having to calculate it without actually doing that measurement, you would do it through Ohm's law. So this works for DC currents, DC circuits only. Okay. So basically, voltage times current equals wattage. Let me not talk about that for a second. Let me talk about the 3 factors: the voltage, current, and resistance. Wattage is separate. So if you wanted to figure out the amps, and you have this wheel or the triangle, look at it closely. Let's say I need to know the amps of a circuit, and I know the voltage and I know the resistance of the circuit. Okay, they gave it to you. That's how they would on the exam. They give you the resistance and they give you the voltage if they wanted you to figure out the current. So you look at the wheel and you say, okay, well, amps is what you're looking for. It's in the middle of the wheel. See, the factors in the middle are what would be the factor you don't know what you're looking for, right? So V divided by R would be I, would be current, So you just take the voltage divided by the resistance. Now, if you look at Ohm's triangle to the right, it's kind of simple to do it with Ohm's triangle, and I wish I could put my finger over this, but let's say if I wanted to figure out the current, what would I do? I take my thumb, I stick it in the outlet. No, I take my thumb and I would put it over the I right there on Ohm's triangle, because that's the one I'm looking for. So if I put it over I, what does it tell me then? V divided by R. See, that's kind of cool. And then if I want to know resistance, I put my thumb and hide the R, and it's V divided by I. If I want to know the voltage, I put my thumb over voltage, and it's I times R. See how that works on that triangle? It's the same thing in the wheel. They just written it out for you. And just as a side note, wattage is a factor that's voltage times current. So it's quite simple. Wattage is a representation of voltage times current. So that's what, they measure light bulbs in that, watts, how many watts, because it's based on how many volts you have, 100, let's say 110 volts out of an outlet or 120 volts out of an outlet, times what? The current gives you the wattage, okay? So, and you can figure it out, power, you can figure out how much watts you have by doing the inverse of that. So that's what wattage is. I'm not sure you have to know anything about wattage, but basically it's very simple. It's voltage times current, okay? And it is on the wheel there as well. Let me give you a couple examples of this. Okay, let's look at these two examples here. I've got battery of 18 volts, okay? Now there's my power supply there, and it shows me the plus and minus of the battery. But in any case, I've got a resistance of 3 ohms and I got a current of 6 amps. So it's already there. That's, those are the 3 factors of that particular circuit, okay? And the one below that, I've got a battery of 36 volts, and I got a current of 12 amps. Remember, current is represented by I, okay, I. And then voltage is represented by V. Sometimes represented by E for energy, but mostly it's V, but you may see something about E, just so you know. The lamp, the resistance is shown in what? By ohms, the ohm symbol, right? So here we go. Let's calculate this one out. I have a battery of 18 volts, and I have a resistance of 3 ohms, and I want to know the current flowing through the circuit. Okay? See, the battery voltage is potential. The pressure is 18. The resistance of the circuit is 3. Now, there's more resistance in just the lamp of 3 ohms. There's resistance in the wire too, but that's minimal. We're not going to consider that, okay, because it's not given to us. But in any case, so I want to figure out the current. So current is equal to E over R, which is the same as V over R. E and V are the same. Energy and voltage is the same, okay? I just wanted to throw that in there because I wanted to make sure that you understand that part of it, if there's an E in something in your equation. The E is equal to voltage. And you come out with 18 volts divided by 3 ohms, and it's 6 amps. Now, if you're going to figure the power there, you just take voltage times current, and 6 amps times 18, that's 108 watts, okay? So here's another circuit. Let's take a look at this. You got a battery of 10 volts. You've got a current of what? I heard you. Okay, 2 amps. Very good. You got it. Now they're asking the resistance. So I look at my ohms wheel there, and what I'm looking for is R. So I go to the middle of the wheel, and I look at R for ohms, and I got a current of 2 amps and a voltage of 10 volts. So my formula would be, I would use probably what? V divided by I. So it's voltage divided by current. So what do I get here? Did I do this already? Is that the same one? Okay, what are we doing here? Okay. Not the same one. Okay. All right, well, let's see. Figure it out. It's V is 10, I is 2, so it's 10 divided by 2. And I get what? That's right, 5 ohms. 5 ohms, okay? So 10 volts divided by 2 amps is, and current is measured in amps, by the way, amperes, okay, which is a large A, okay? And voltage is V, which is a large V. And then, of course, again, the ohms, resistance is measured in the ohms, and it's actually that upside down horseshoe, okay? So here's one. Battery is 18 volts. I don't know the current. I know my lamp is 3 ohms. So no, we just did that or something? I don't know. The answer is 6A. Okay, well, how did I figure that out? 18 volts. My formula would be what? V divided by R. So 18 divided by 3 is 6. Right. Okay, here's another one. I've got 12 volts. You're going to need to look at your sheet here. Okay. I mean, you can do it let's take this one. 12 volts. I know the current on this one is 6 amps. I'm looking for the resistance. So I'm going to use, yeah, I can do this here. Let me see. Okay. So what I can do, here's how you do this. So in this circuit, I'm 12 volts and 6 amps. I'm looking for resistance. So I just cover up the R. And I cover up the R here, and then it tells me voltage divided by what? Current, right? See, that line is a divided line, and that line is a multiplied line. So if I was looking for current, and that's the one I didn't know, I would have to know the voltage and resistance, so I'd cover up the I, because I'm looking for current. It's the unknown factor, so it's V divided by R. If I was looking for voltage, I would cover up the one I'm looking for, which is voltage, and it's I times R. See, that's kind of neat there. And it's the same in here. It's what you're looking for is on the middle here, and then they've already written out the formula for you. But this is just as simple. It just doesn't have power in there. But you know power is current times voltage anyway, and I don't think that'll be on the exam. Okay, so this is two different ways of doing it. It's the same thing. It's just a little easy way to do the formula if you cover it up here or if you look down in here for the factor you're looking for. Okay, let's jump back up to this view. All right, so this would be what? What is it? Voltage by current. So where was I? I forgot my thought here. I can hear you all yelling the answer out now. So I'm looking for R covered up. So it's V divided by I. V is 12 divided by 6, which is I, 6 amp. And by the way, it's got to be in amps. It can't be in milliamps or anything. You got to convert it out of milliamps or whatever it's in to amps. Everything is calculated in volts and amps. Okay. Now, I don't think you're going to have it in a different, like milliamps or anything like that. So it'll say amps next to it. So it's basically 12 divided by 6. What did you say? 3? That's not right. All right, there's somebody said 2. Okay, good. Yes, it's 2. One more. Let's do one more or 2 more, whatever we got on the thing here. All right, so we've got volts equals what? We're looking for our voltage here. And I'm going to do this simple way. I'm going to take this and little thing here. I'm looking for volts, right? So I'm going to cover up my V. Oh, that makes it easy. What is it now? It's I times R. So it's 1 amp times 2 ohms. So the answer must be what? 2. 2 what? 2 volts, right? 1 times 2 is 2, right? Okay, now let's talk about something here that's more likely going to be on your exam. It's battery capacity. Now, in our trade, we're always, with the alarm business, fire alarm business, you always got to have a backup battery source for even telecommunications, all that stuff. You always need a backup battery in case the power goes out, right? You got to supply the system with current while the power's out until it comes back on. So a lot of times you've got, especially with fire alarm systems, you've got, and even burglar alarms, you've got to calculate out the amount of time the battery will last under load, okay? Because you're required by certain insurance companies and regulators, UL, Underwriters Laboratory, Factory Mutual, those guys, that your systems have to meet a certain requirement in order to get a discount or on insurance and things like that. So the banks and everything, they have their systems so that if the power goes out, they have batteries in them that will run the system for a predetermined amount of time under continuous load, okay, and under non-load too. And this is all part of the requirements. And some of these requirements are in the UL books and so forth. But in any case, so you have to know as a contractor, you have to know battery capacity. Obviously most times the larger the battery is, the more capacity it has, right? The more current it has, not the voltage. Voltage is not, that's just pressure. Remember, that's not that doesn't determine the size. You can have a 12-volt battery real small and a 12-volt battery real big. But the larger the batteries are, okay, the larger the batteries are, that kind of determines the amount of current, right? Because you're always trying to keep things small, so you're going to make them so that they produce the most current at the smallest possible size, right? So a cell phone, 12 volt cell phone battery is going to be 12 volts, but it's, it's small. It's got very little current in it available, right? But a big 12 volt car battery, that thing's got some amps in it. It's got some current in it. So, but so you can kind of look at the size of the battery and say, well, that's got more current than that other one does. So that's just something you should keep in your mind. But for backup systems, amp hour capacity is important rating to know. The rating is based on the total number of amperes the battery can supply in a given period of even withdrawal. A battery with a capacity of 1 amp hour should be able to continuously supply a current of 1 amp to a load for exactly 1 hour, or 2 amps for a half an hour, or a third of an amp for 3 hours, okay, before becoming completely discharged. Accordingly, a battery rated at 100 amp hours can supply 5 amperes per hour for 20 hours. If more than 5 amperes per hour is taken from the battery, it won't even supply its 100 amp hour rating. Okay, what did we just say there? Let's see. Okay, let me try to make it simple for you. Okay, on a battery, you have a rating of voltage, and you have a rating of amps per hour, okay? Not amps, but amps per hour. The thing is, you don't know, when you have a battery in a circuit, you don't know, you don't know what okay, I'm confused myself. A battery has a certain amount of current in it, okay? And that's based on how much it can supply in 1 hour, all right? That's called amps per hour, amp hour. So when you look at a battery, you see a rating of 12 volts, or whatever the voltage rating is, and you'll see H, a large A and a small h. That's amps per hour. That's not current. It's current available per hour. And why do they do it that way? Because they don't know what the draw is on the circuit. Okay? So they have to tell you how much current is available in the battery, and they have to base it on something. So they base it on a draw of an hour. Okay? 1 amp hour, wherever it's 14 amp hours. Whatever the amp hour is, that's how much current it can supply in 1 hour. So a small battery might not even have a half an amp per hour. A larger battery might be able to supply, 12 amps per hour, something like that. It just depends. Okay, so that's called amp hour rating, and so it's really not current. It's current per hour that's available. Okay, and why is this important? Because it comes down to the fact of calculating out how much you can supply to a load based on the draw of that load, okay, over a period of time based on the amount of amp hours that is being supplied by the battery you're putting in. Okay, and this kind of stuff is on the exam, and it's a little complicated when you look at it, but once you understand this, you should be okay with it. So here's a question, typical question. How many hours before this battery dies? Now, one thing you have to look here, you see 12 volts, 8 amp hours. Now, don't get that confused with a circuit that has 12 volts and 8 amps running through it, okay? That's not the case. It is an AH. Okay, that's amps per hour. That if it was just an A, that would mean that circuit has got that 500 ohm resistor is pulling 8 amps. Okay, so if it has an H, little h by it, it's not. That's showing me that's a battery. Even if it didn't tell me that's a battery, I can see that's a battery. Why? Because it's got an AH next to it. So that's amps per hour. So that's a battery. Okay, that's not a power supply. It's a battery. Okay. But anyway, regardless of that, what people do, they look at that circuit and they get confused because they think, well, the circuit's got 12 volts, 500 ohm resistors, it's pulling 8 amps an hour, and they try to figure out that draw on that circuit and how long the battery's going to last. But there's no way to do that. What you're looking at there is a circuit with 500 ohms resistance on the resistor, and you're looking at a battery with 12 volts and 8 amp hours, right? Okay. So what's the deal there? How do I figure out how long this battery is going to last before it dies? All right. What am I missing? I'm missing something. I need to know something. I know the resistance. I know the voltage. 8 amp hours is what my supply has available. I'm missing what? The draw. I'm missing the draw of the circuit. Meaning I'm missing the current draw of the circuit, right? So basically, I need to figure out what this circuit is drawing. What is it pulling from that battery? Remember, voltage, Ohm's law, you've got volts, resistance, and current, those three factors. I don't know the current here. I have to calculate the current, right? So how do I do that? Well, Ohm's law tells me voltage divided by resistance equals current, right? So I have what? I know I got a battery at 12 volts. Obviously, the power supply is 12 volts, and I got a 500 ohm resistor, right? So I take 12 divided by 500, and I get 0.024 amps. So now I know, and that's in amps now. It's not milliamps or anything like that. So it's amps. So it's because if you take voltage and you do the formula, it always comes out in amps. All right. So basically, my circuit, that resistor could be a light bulb, whatever. It's just a resistor, meaning showing a resistance. It could be a light bulb. Light bulb has resistance. That's how it glows. When you have a light bulb, you're pushing current through a very thin filament that's in an enclosed glass envelope that doesn't have any oxygen in it. And when those electrons bounce against each other, they cause them to heat up. Well, that heat, that resistance causing that electron to heat up that tungsten or whatever the material is, gives off photons of light, and that's where you get the lights from. So basically, a resistor could be anything. It could also be a load, just some kind of load, a heating element or something. But they show it as a resistor, okay, being a load. So here's the situation. You've got 500 ohms resistance of load with a 12 volt battery. It's pulling, those resistors is pulling 0.024 amps through the circuit based on your load of 500 ohms and 12 volts. Now I know it's 0.024 amps being pulled through that circuit, and I know that my battery can supply 8 amps an hour. So how many hours will the battery last? So I figured that out. So what do? What's my next step? All I do is take 8 amp hours and I divide it by the amount of current being pulled out of the battery, which is 0.024, and I come up with 333 hours. Okay, that's how simple it is. But you can't get confused you can get confused, I say, that you see that 8 AH there and you think it's current going through the circuit. No. When AH is written there, that's amperes available per hour. Nothing else represents that except the battery. So you know right away when it's at AH, it's a battery. If it had just an A next to it, it's the amount of current and probably going to be in the circuit, So that's how you do that. Let's take another one. Here's another. This one's actually, what's the difference between that 1 amp hour and the 8 amp hour? Probably going to be a smaller size battery, right? Because it's got, less current it's supplying. So it's a little smaller probably than the other one. Actually, it's 1/8 of the time smaller, right? So if this one was this big, this one here, the 8 amp hour is like a very typical alarm battery. The older ones, they used to be 8 amp hours. Now they've got them down to like 4.5 because their drains are a lot less. But in any case, so you've got 12 volts, a 1 amp hour battery, 12 volt, 1 amp hour battery, and we got more resistance here. You got a 1,000 ohm resistor. So they're asking how many hours before this battery dies. Okay, so what don't we know? Right, I can hear you. Yeah, we don't know the current. We don't know the current of the circuit. So we got to figure out the current. So we use our wheel there, and we don't know the current. So the current is measured in amps. So the formula is V divided by R. So it would be what? 12 divided by 1,000, right? So 12's on the top, 1,000's in the middle. So boy, that's going to be a dot something, isn't it? It's dot 012 amps are being pulled from that from that battery, being taken out of that battery, okay? So I've got a 0.012 amp drain on the battery, and the question was, how long will that battery last? I know it's going to supply at least 1 amp per hour, okay? So I just divide then what? 1 amp hour divided by 0.012 amps, and I get 83 hours, okay? So just remember, very important, remember that AH means amp hours. It represents a battery that can be, with the current being supplied. So that's how much current can be supplied from that battery. And if you have it in a circuit and you got to figure it out, battery drain, which is probably going to be on your test, you've got to know that you've got to calculate the current of the circuit, because that's what's sucking the amps out of that battery, right? Okay. Now let's talk briefly about, and I just want to explain this to you. You may probably already know this, obviously, but it's important to understand there's an inverse relationship when it comes to wire size, and it's kind of confusing. And I hated the fact that it's this way, because even me, I have to think about it sometimes. But American wire gauge, which is a standard, by the way, we use AWG in the United States, okay? So, and that's basically 36 size conductors through 4/0 or 40, which is a gauge size, okay? So there's 40 of these AWG sizes of conductors, at 26, 12, 14, different things like that, okay? So the smaller numbers of AWG represent a larger conductor size. So the smaller the number, the bigger the conductor, right? Kind of backwards there. But the reason for that is, and I'll explain it to you, is that, and I don't have my, actually I do. Just give me 1 second. I see it over there. Let me just grab it. Okay. This is, I just happen to have the box over there I take to my workshop. I just like to show this. This is a rubber band, obviously. So basically what happens with wire is that it is drawn through these dies, and each time they draw it, like for example this rubber band, let's say it comes in a square ingot, and it's pulled and stretched. When you stretch it, see it gets thinner and thinner, just like bubble gum, just like this elastic rubber band here. The more I stretch it, each time I stretch it, it goes down a little bit thinner. So with wire, you can't just stretch it because it breaks. So they heat it up and they stretch it and they pull it through a die, and each drawing time, each time they draw it, each time they stretch it, is one draw. And that's where they've got all these numbers from. So basically, if it's a 4/0, it's been stretched 4 times. If it's a 26/0, it's been stretched 26 times. Okay, so that's why the higher the number, the smaller the diameter size. The smaller the cross-sectional area. So the more draws you have, the smaller the wire goes. It's an inverse relationship. So you would think that when the wire gets bigger, they would make the number bigger, but it's not. It's just the opposite. So it's a little confusing. So for example, if I had to bond a pool for some reason, bond a pool or bond anything with, according to the NEC, it has to be a 6 AWG, 6 American wire gauge. So I'm out there and I'm bonding this alarm system or something, or whatever it is, and I don't have a 6 AWG in my vehicle. Okay, so but I do have a 4 AWG and a 10 AWG. So by code, which one could I use? The 4 AWG. Yes, the number's smaller, but the wire is actually bigger, right? Because it's an inverse relationship. So if you look onto this graph here, and this is what you need to know, different sizes of AWG, American wire gauge, right? So obviously, the lower the number, what happens to the resistance? The resistance gets less, right? because the lower the number, the bigger the cross-sectional area, right? You know, so, and that's why when you got like 4 odd or 4 double zeros, what happens is, you know, whenever you see big conductors, they're never solid, okay? Because a solid conductor is very hard to bend. So that's why they're all stranded, because the stranded conductors, you can got more flexibility out of them. So you never see a big power conductor or anything like on a pole or anything like that as a solid conductor. It's always a stranded conductor so that they can, you know, somehow bend to things. Some of those things are really big. After that, I think it goes to cross sectional mills or something, or goes, you know, there's a different number when it gets into really, really big wires and so forth. But in any case, so when the wire number gets bigger, what happens? The diameter of the conductor gets smaller. And that's going to mean what? More resistance, right? So here it is. Decreasing American wire gauge, increasing wire diameter. Decreasing American wire gauge number, decreasing resistance, right? Okay. So, and this is important when it comes to things like, what you need to understand is, and like for the UL and UL book, it gives some references to this, but you as a low voltage installer, service person, and so forth, taking this exam, you need to have an understanding that if you put a bell in the back of a warehouse, okay, let's say it's some kind of a bell for something, alarm bell maybe, and since a bell pulls quite a bit of current, and let's say you put it 150 feet, and you use a number 26 conductor cable, okay, you might not be able to supply all the current or voltage that bell needs because of the fact that there's a lot of resistance on that smaller conductor. You might have to do what? Increase the conductor size. So now that doesn't mean increase the doesn't mean increase the number, right? The number is going to be smaller when you increase the conductor size. Okay, it's the inverse of that. So you know, because conductors, the longer you run them, what happens? The more resistance, right? Because they're a resistor too. They're just a long resistor, even though if it's copper, it's still got some resistance in it. So the longer it is, the more resistance it has. The more resistance it has, it affects Ohm's law. You know, you can figure it out. You know, you measure the resistance, and that's what they tell you when you look at the like belt and cable and stuff. They tell you the resistance per foot. You know, yeah, per foot, yeah. So you can actually figure it out if you calculate. Well, okay, I'm going to put a bell back here. What size conductor do I need? Because I'm running at 150 feet and I've got so much resistance per foot. I know I got to supply 12 volts. How much current do I need? You know, for that. Or, you know, so I mean, because obviously the bell runs off a certain voltage, so you're going to have the voltage constant. So the resistance is going to be constant because you're running the footage out to that point, so you can calculate it. Your current load. And if your current depends on, now you got to look at the conductor size to see how much current a conductor can handle based on its, what, AWG number. Okay, and that's all in NEC. All right, so that's all part of calculating, you know, loads and everything like that. So, whoops, oh boy. Okay, why I did that, I have no idea. There we go, we're back. Okay, cable types, I'm going to go over these briefly. Solid and stranded cable types, right? Stranded cable types are more flexible than solid. Of course, solid conductors are less expensive. There's some attenuation when it comes to solid conductors and so forth versus stranded conductors as well. That means you know, it's got like attenuation would mean kind of a loss of signal strength along the conductors. Okay, so you know, there's two types, solid and stranded. Remember that. Twisted versus straight lay. Twisted conductors are what? They're twisted about themselves, like category cables, category 5, 6, 7, things like that. 7, do they have 7 yet? I'm not sure. I know they have 6, and augmented 6, but they may not have 7 yet. Okay, so, and those twisting of the cable helps do what? It helps reduce crosstalk, interference, because when the cables are twisted, they cancel out the crosstalk between the cable pairs. Okay, now that's not something you really need to know, but you know, in telecom, that's important to understand. Shielded versus unshielded cables. Okay, shielded cables, those are cables that got some kind of a shield over them, a wire braid or a foil shield that stops them from receiving RF, radio frequency interference onto the cable. This is mostly for signaling cable, like communication cables. Alarm cables it's not a big issue with, but signaling cables, That's why, remember I said earlier, one of the exam questions was what? When you cross a cable, a low voltage cable with a high voltage cable, you cross it at what? A 90-degree angle, right? Because you don't want there to be any, an alternating current piece of Romex cable, standard Romex in there. There's a magnetic field around that, all right? It's a small magnetic field around it because the alternating current's going back and forth in that wire, producing a little bit of magnetic field. So if you cross that with a, with a low voltage conductor, a signaling conductor, like a communication conductor, that magnetic field can be induced into that conductor and can cause issues, signal issues, attenuation, frequency problems with that. So you want to avoid that. That's why you don't put your communication conductors over the top of fluorescent lights or ballast, because those things, those ballasts there that are taking that, remember the 120 volts and making it thousands of volts so it can arc that tube, that's got a huge magnetic field around it. So you lay a communication conductor across that thing, you're going to have all kinds of signaling issues. So you want to avoid that. Now, what is the best shield? It's a piece of conduit, a metallic piece of conduit, metal conduit, and that's been on the exam as well. Okay, what's the best shield? Metal conduit. Put your conductors in metal conduit. It's the best shield, grounded at one end. Okay, so anyway. Well, grounded at least one end. Okay, so shielded wires, EMI, electromagnetic interference, that acronym EMI you should know. RFI, radio frequency interference, you should know that as well too. Okay, different kinds of stranded and solid conductor markings here. UL, Underwriters Laboratory, they mark conductors. CMR is communication, riser cables. I'll explain that in a little bit later. And you can see an example here of some stranded conductors here. Now this is not twisted pair. This is not conductors that are twisted because of wanting to reduce crosstalk. This is just the actual metallic members, the strands being twisted, okay? So there's a difference between twisting the insulated conductors. That would be like category cable. So what you need to know here is, what does 22/2C mean? What is 22? The AWG number, right? The size. This is what's marked on all cables. 22 is AWG number. 2 is the number of conductors. Okay? I'll explain CMR later when we get to further on in this presentation. Solid conductor cable markings here. These are twisted pairs. The insulation is wrapped around each other. See that? Okay, they're twisted together to reduce what? Crosstalk, right? Okay. This is a what? 4 pair and 24 AWG. That tells me the gauge size and how many wires are in the under the insulation sleeve. Okay. All right. So let me just briefly read this here. A cable shield is a metallic outer covering around insulated conductors, usually made of foil or braided metal strands of tinted copper, aluminum, or with another conductive alloy such as metallic solid or flexible conduit. Cable shields reduce the electric magnetic radiation and interference being emitted from the cables and increase the cables per unit length of the cable, the capacitance per unit length of the cable. In addition, when a shield is properly grounded and bonded, it reduces the possibility of electrocution. Here's an example of it looks like a coaxial cable here. Okay. Here's a braided shield on a coaxial cable with a foil underlining there. And dielectric, what is a dielectric? That's been on the exam before. A dielectric is an insulator, okay? It's a form of an insulator. Means insulator. A cable drain wire. This is terminology you should know. A drain wire is a metallic conductor frequently used in contact with foil-type signaling cable shielding to provide a low resistance ground return to any point along the shield. The drain wire and cable braid are both part of a cable shield and are electrically connected. The drain wire allows for ease of termination of the cable shield, for example, when crimping or soldering or punching down. So basically, the drain wire connects to the foil, which is the shield. And in order to terminate it, you're obviously not going to be terminating the foil very well, so you use the drain wire for termination, okay? Then you've got messenger wire. What's a messenger wire? Well, that's a wire that is a metallic supporting member, either solid or stranded, which may also perform the function of a conductor. Yeah, maybe a ground. But in any case, a messenger wire is to support your strands between poles in the building, between poles and poles. You can't just put a piece of copper wire there because it'll stretch. Copper's not, it has a lot of, stretchability to it, copper. So you got to put some kind of a steel wire with that, and it's called a messenger wire. And it's attached to each side of the poles or the building and so forth, and it supports the strand so the wire and cable doesn't stretch, okay? So keep that in mind, messenger wire. We've already talked about all this. Oh, plenum cable. Okay, let's talk about plenum cable. Plenum is the cable that is laid in plenum spaces of the building. The plenum is the space that is used for heating, ventilation, and air conditioning systems, typically between the structural ceiling and the drop ceiling or under a raised floor. The plenum space is typically used to house the communication cables for the building's computer and telephone network. However, okay. In buildings, commercial buildings, you have these areas that are used for the return of air that people breathe, okay? And those are referred to as plenum spaces. Now, it could be a duct, an actual metal duct of some sort that has a return attached to it, and that inside there would be considered plenum space. But more so than that, and what we're really concerned about, is keeping our conductors and wires out of plenum spaces unless they are rated to be plenum rated for fire, retardancy and low smoke emission, okay? Or they're in conduit. So a lot of times in the business, you would have a situation where you have a drop ceiling, okay? And it'll have grates in the drop ceiling, but there won't be any ducts in there. They'll maybe have a grate at the far wall, and so they use that entire drop ceiling as the return for the air. So the air that goes up into that drop ceiling is all considered plenum and is in this plenum space then. Because you don't want to put wires in that space if it's plenum. Now, not all drop ceilings are plenum, okay? Most of them aren't, but some of them are, meaning that some of them are used for the return. Not a return that has a duct in it. That's not the issue. It's when it doesn't have a duct in it and it just has a grate, and then you have a grate, like say at the very far wall, and you're using the hole inside of that area above the drop ceiling. You're using that as the plenum space, and you're sucking the air from there through the grate that's on in the drop ceiling. And I don't have a good representation of that here, I don't think, to show you. But in any case, what you have to remember, though, in those spaces, you're required to put plenum cable, or the cable has to be in conduit. Now, plenum cable is more expensive. However, it's been tested, certain kind of insulation material and so forth, and basically it's going to produce less smoke, less toxic smoke, and it's going to burn slower, okay? So, because what you don't want to have happen is you get a fire up there in those drop ceilings, or in an area, and guess what happens? All that smoke is drawn into the heating and ventilating system, right? The HVAC system, and it's pumped out through the rest of the building. And of course, what's that going to do? You know, smoke is what kills people, even most of the time before the fire does. So you have to know about plenum spaces. You have to know that in plenum spaces you need to use plenum rated cable, or the cable needs to be in conduit. Okay. And this is based on fire safety rating. I'm not going to get into all this. But plenum cable is, the suffix is P, and I'm going to show you this. Okay, so P means plenum. It's at the top of the hierarchical chart, meaning it's the best cable you can get for fire retardancy. Okay, it just doesn't burn very good. It doesn't cause a lot of smoke, and the smoke is not toxic, and so forth. Then below that is what they call riser cable. Then they have general cable, and then they've got underfloor cable and stuff like that. But basically, the suffix is you have the acronym, then you have the suffix. The suffix is at the end of the acronym. So if it's a CMP, CM represents communication, P represents plenum, so it's CMP. That tells me it's communication cable, Article 800, communications cable, right? And then P, plenum. Okay? So let's just jump ahead here. If you want to look quickly at these testing of these cables here, kind of shows you how they test them. The Steiner tunnel test. Anyway, all these cables are rated based on smoke toxicity, heat release, and so forth. Okay, so here you see MPP, multi-purpose plenum cable, CMP, communication multi-purpose or communication plenum cable. Now this is okay. Let me explain something here, which is another issue. And I've given you this in your supplementary sheets. It's right here. Okay, this is the hierarchical chart for cabling. And then I gave you a substitution that's allowed on the back. Now, you really don't need this. I gave it to you as if you don't understand this. But basically, take a look at this. Take this out. Take a look at this. And I'm going to explain something to you here. I'm going to actually go to the chart that's on the overhead here. Now, okay, this is before 2005. They were using MPP. If you look at your paper here, you can see the very top left-hand side is multi-purpose plenum cable. All right, they're no longer, after 2005, they stopped naming a category for multi-purpose plenum cable or riser cable or general cable. So MP, multi-purpose, is no longer a acronym that you would see in the National Electric Code. However, the exam still has a question on there with MPP, okay, multi-purpose plenum cable. And obviously you need to understand, and that's why I gave you this chart, which is from, I think, 95 or something like that. But anyway, because it's on this chart. Because a lot of times what this exam testing company does is they don't go back and remove old questions. I noticed that. I've seen that with the telecommunications book and that. So if there's any kind of change, a lot of times they don't pick it up and they just keep asking the same question. And if people keep getting it right, they don't even get flagged. So in any case, one of the questions is multi-purpose cable. And so it's MP. So it's not in any of the sections of the NEC. It is just basically on my chart there. So how does this work? Let me explain to you this sheet here, and you can look at the overhead here, or you can look at your sheet, either way. You see across the top, it says NEC articles. These are chapters in the NEC. 800 is communication. Okay, 725 is class 1, class 2, class 3 remote control, signaling and power limited circuits. Okay, what is that? 760, that's fire alarms. All right, 770 is optical fiber cable, and so forth. I think 830 is network broadband communication conductors. Okay, so those are those are chapters, and those are the below them in row below them are the cable types that are used for those articles. Okay, like CMP, that's communication. CM means communication. P means plenum. Okay. CMR means riser, CMR, communication riser. So you've got the acronym first, and then you've got the fire retardancy last. So P is the top. Below that, you can see everything is a riser cable, which riser cables do have a higher flame retardancy, and they're allowed to be used sometimes in vertical shafts and things like that. But they're less expensive. They're called riser cables. And below that, you have general purpose cabling, okay? And then you can have residential, and then you can even have under carpet cabling. The point is that you cannot replace, if the code requires you to put in a CMP or a CATVP or a plenum cable, you cannot replace that cable with any other cable, with a riser cable, with a general purpose cable, or any other cable. But if the code requires you to put in a riser cable, you can replace that with a plenum cable. You can replace what's below with what's above, but you can't place what's above with what's below, because if the code requires you to put in a higher rated fire retardancy cable like plenum, you can't just put a lower cable in that's below it. Okay, and there's nothing above plenum. So, but if the code requires you to put a riser cable in, well, if you want to put a plenum cable and spend the money, you can do that. You can put a plenum cable in there, no problem. Or if it's just a general purpose cable, which is below riser, you can put a riser cable in there. You can put a plenum cable in there too. It's fine. But you can't put a residential cable in a general cable or underfloor carpet cable, depending upon the code. So these are your article numbers. So what you have to remember about this is the end of the actual acronym, the end of the acronym, okay, the P and the R and the G, which is general purpose, or it might not have anything on the end of it, then that means that that's the flame retardancy levels, and you have to keep them at whatever that is, or you have to put in something above that, more flame retardancy, okay? So you can quite simply look at this, and what the exam is going to ask you is, and I'll show you this in the NEC, what the exam is going to ask you is, it's going to ask you about, it'll ask you a question like, you have a CMP cable, what can you replace it with? And that's a communication cable, right? CMP, communication plenum, and it might say, CMR, it might say CATV, and then it might say FPLP. Now you can replace a CMP with an FPLP because it's got the same flame retardancy. Maybe you're using it, or like you say, a CMP, which is twisted pair, right? And you want to replace it with an OFNP, optical fiber cable that's non-conductive, but it's plenum. The plenums you can replace. You can replace any of these together, but it's got to have a P on it. All right? That's simple. It's simple. It's very simple. You just understand you can't replace anything up here with anything below. You can't place this with anything below. You can't place this with anything below, but you can replace this with what's above, this with what's above, and so forth, okay? So obviously the plenum cable is more expensive, but why do you use them? Why don't you put all your wires in conduit? Well, conduit's a lot more expensive than plenum. If you got a lot of wires to run, you can put everything in conduit, but it's going to be expensive. So we have plenum cable now that we can use. Because why? Because when these plenum spaces catch on fire, that cable, and this is what's been happening over the years, and I don't know if I go into detail on this in the workshop, but they catch on fire, they cause a lot of fumes, they're sucked into the heating and ventilation system, the air conditioning system, and they're pumped throughout the building, and people die. So they've now restricted the cable types. Years ago, they started putting these cable types together, and because it's not so much the smoke or the heat, it's what the toxicity of the insulation that's burning. They found out that stuff is extremely toxic. So people breathe that stuff and they're gone. So I mean, it's like that's why they do that now. So you know, you have, and that it's real big with fire alarm systems and everything, and you got to be careful about all that and make sure you got the right conductors in there and so forth by the code. Okay. And this is just a cable hierarchical chart here. It shows them all, and that's plenum, and then you got substitution and so forth. So fire stopping, I'm going to briefly touch on this. Basically, what fire stopping is. Let me just say the simple part. A fire stop is simply a hole that has been made in a fire-rated barrier in order to run some form of building service, for example, conduit or cable. A fire stop system is simply a patching method used to seal up the hole and restore the barrier's fire rating. That's all it is. You have basically what we're concerned about is electrical penetrations, electrical through penetrations. If we're going to run our wires through a firewall, what is a firewall? Now, this has been another question. A firewall goes from the ground floor all the way up, not just to the drop ceiling, but all the way up to the roof, okay? Because you're trying to seal the smoke and flames and that from getting into the other rooms or other compartments or other buildings. So you have a fire stop there, and these fire stops are rated. Standard drywall fire stop can be, 2-hour rating. Okay, that's a standard one in like a strip mall between the units. You'll have a firewall. It goes from the very ground floor all the way down on the floor, all the way up to the roof, and sealed. So if you penetrate that with a hole, then you've got to put some kind of fire stop material in there, which has been rated by either UL, Factory Mutual, or another fire stop rating company. And basically you take a picture of it and you catalog it and everything else so that you've done it right, because it's all relates to life safety, because this stuff can, don't do it, it can kill people. So you have to restrict that smoke and that heat and that flame from going through that firewall. So if you penetrate that firewall, you've got to put the sealant around it. It could be cement. There's mechanical fire stops and there's non-mechanical fire stops. Okay, so a mechanical fire stop is actually a mechanical thing that you put the wires in. You kind of, it's got fire stop material in there, and you lock it down on the wires. And usually they're expensive. They usually use them for a lot of cables, but basically. Non-mechanical would be some kind of cementitious material, maybe a putty or something, that not just regular putty, not just regular caulking. It has to be rated fire stop material and so forth. So that's all you really need to know about that. That if you penetrate a firewall, you're responsible to make sure you put the fire rated material in there to seal up that hole so you don't have an open on a through penetration. Okay. So again, there's mechanical and non-mechanical fire stop methods here. Here's a mechanical fire stop example, what I was telling you about. Okay, another one. In the Bixby Telecommunication Distribution Methods Manual, there is a section on fire stop, and it's installation manual, basically, that section. And it shows you all different types of fire stopping materials and ways to do it and so forth. It's pretty good, actually. But you really don't need to know on a specific type of fire stopping and how to do it. What you really need to know for the exam is basically that if you penetrate or somebody penetrates a fire stop, you have to bring it back up to the rating of that particular fire barrier, whatever it is, and it has to be with pre-approved material that is tested and already rated and been approved for use. Okay, and I think I've got some pictures in here. I'm not going to get into too much, but this gives you a good example of a through penetration here and a 2-hour fire rated drywall assembly. Okay, and this looks like a sleeve of some sort, piece of pipe or something going through there. See the darker fire stop material there? That's all you have to do. Seal it up with that and so forth. Okay, here's an example. different ratings and so forth, not important. This is obviously a firewall that somebody has penetrated, but there's no fire stop material. I'm sure you see this all the time because I don't know, some people get away with this and it's really bad. I mean, here's somebody that looks like it took a hammer and just busted through the wall and didn't put any kind of fire stop material in it whatsoever. Okay, that's a code violation, and it has to be the specific. It has to be the right material. You can't just be concrete or any kind of putty. It has to be. That's why it's so important. Many times they take pictures of it and you actually tag them. Okay, you put a tag on it. I'm not going to get into all that, but I mean, this is life safety you're talking about here. So if you don't do that and something happens, they might come looking for you. And there's a lot of attorneys out there that like to make money off of things like this. So if you wind up being in a job where there's a fire stop, you don't fire stop that material, and then they wind up turning around and blaming it on you or your company, it can be devastating. Okay, so here's just some of the ways they test it. Here's a tag. This is a typical fire stop tag. Okay. And now let's just briefly talk about demarcation points. What is a demarcation point? Well, this is where the service provider, like a phone company, comes in and terminates at the premise. Okay, it's called a demarcation point. It could be like an RJ31X jack or some kind of interface that allows disconnection of the system by the phone company or the service provider, so they can work on their tester circuits. Okay, it's an FCC regulation. The reason I'm bringing this up is there is a question, and this has been actually on the general exam too, and I don't know if it's a dummy question for them or not, but they ask a question about wiring up the RJ31X jack, and this, I've given you this is in the telecommunications book. It actually doesn't look exactly like that, but it's the same kind of design. There's all the jacks are listed there, and what they do is they ask you a question: what if you hook up wrong the modular jack, the RJ31X jack? What if you put it on pin so and so and so and so? What happens? And the available choices are phone works, alarm doesn't work, several choices with the alarm system and the phone working or not working. Okay, so if you've ever been in the alarm industry for any period of time, one of the standards for many years is, especially residential, is the RJ31X jack for the digital dialers. All right, so nowadays, we have demarcation points, but basically a lot of times, now the alarms are being actually monitored through the internet or radio or cellular or something like that. But in any case, there's just many digital panels still being used today. Don't get me wrong, but they need dial tone to dial out and communicate with the central station. So basically, in your situation here, you've got the CO lines coming in. That's the central office lines from the telephone company. T and R is tip and ring. That's where you have your dial tone, your 2000 cycle tone on there. It goes to the RJ jack on pin number 4 and 5. It goes through that jack to the security or fire alarm system on pins 4 and 5. Then it comes out on pins 1 and 8, and then it goes to the house phones. Now there's some jumpers in there. You see those little arrows there with the little jumpers. That's in case the jack is unplugged. It basically shorts the CO lines coming in from the central office directly to the phones. And the reason that RJ31X jack is required is so when there's a trouble with the circuit, the phone company can come out, unplug your security or fire alarm, and they can test the circuit and make sure it's not your security or fire alarm system that's causing the problem. Why do we drag that phone line through our fire and alarm panels? Well, first of all, we got to dial out through those phone lines, but we're supervising that phone line. So if the alarm goes off, the panels disconnect the house phones and seize the dial tone and communicate that way, so that nobody in the house can pick up the phone and disrupt the signals going out to the central monitoring station. Okay, so it's a supervision type thing, and if you hook it up wrong, you know, you got a problem. Okay, so my question on my exam asked that question: what if you hook it up wrong? Now, let me show you some. So if pin 4 and 5 is the hot coming in from the CO, the tip and ring, the actual voltage on the dial tone. If that 4 and 5 gets hooked up to 2, 3, 6, or 7, those are blank. They don't go anywhere. They're just dead. They're just on the terminal block. Okay, the terminal block looks like what? Like this. That, remember? Some of you remember these, I'm sure, or you're doing these all the time. That plugs in this. That cord plugs into the jack, and when it is plugged in, those jumpers in there come off and automatically release it. But in any case, you're just going to have to figure it out. And that's usually a question on the exam. You know, you could have the phones and the alarm panel working. You could have the phones working, no alarm panel. You could have no alarm panel, and you could have phones. Say that right? Well, in any case, or you can have neither one of them working. You got to trace the dial tone coming in on the tip and ring and see what happens to it. If you hook up number 4 to number 3 when it comes in, right? Well, it's not going anywhere then, so what's going to happen? You're not going to have any dial tone for the phones going anywhere. No phones, no security panel, right? Because you've hooked up the ring side of the CO lines to pin 3 or pin 2, those are all dead. Or if you put it on pin 6 or 7, those are all dead circuits. They don't go through, right? If I hook pin number 4 coming in from the ring on the CO lines, I hook it directly to number 1, what's going to happen? I'm going to have phones, but I'm not going to have security because it's not going, that side's not going into the security. So basically, this is just a block pin diagram of the jack, and remember that the CO lines coming in from the central office have the ring and tip on them, and they go through the alarm panel, and then they go to the phones, and just, you know, there's just relays in there. And if the alarm goes off, it disconnects the R1 and T1. It disconnects the house phones, and they stay on lines. CO lines T and R, and they dial out. Okay, this has to be hooked up right, or the system's not going to work, or there's going to be a problem. And this is important because this is supervision. Because if you hook this up wrong, worst case scenario would be that you don't notice it because you paralleled the tip and R1 and or tip and T1 and R and R1, meaning you parallel the CO lines to the phone lines, and that means that the security system will work and the phone will work. But when the security system goes into alarm, it will not disconnect the phones. The phones will still be on top of the line, and if somebody picks up the phone or drops and pulls it off the hook or something, you're interfering with the signal. You can, if you guys, some of you guys have been in the alarm business for a while, you can tell that right away, because if you're sending a signal from your alarm panel and you pick up a house phone and you hear it dialing out, well, guess what? You've got you don't have supervision of that line. Those phones aren't disconnected. When you trip the alarm panel, those phones should be dead, okay? Because, but if you trip the alarm panel and you can listen to the handshake and the signals and the kiss off from the alarm panel to the central station, you can hear it on the phone. That means that phones are tied into parallel on top of those tips and rings. And that's a problem, because if Granny is on the phone and the house catches on fire and she drops the phone and it's off the hook, if that panel can't disconnect that phone, that means it's not going to get dial tone. That means that phone is going to be, sitting there off hook, and it won't be able to get dial tone because the panel cannot release the phones and seize the dial tone to dial out. That means, guess what? If there's no dial tone, the system is not communicating to central station. And that means, Granny burns to death I shouldn't have said that. But I mean, that could be a problem. Or she's got a medical alarm device, and she's on the phone, and and it hasn't been hooked up right, and she's talking to somebody, or presses the button, and she goes to the phone to try to call, and she knocks it on the floor. Well, that seizes dial tone. The system can't. Maybe it seizes it for a while, and it goes into the mode. And then this thing tries to get dial tone. It won't get dial tone, and it can't dial out. So this kind of stuff could be life safety issues. So you got to know how to do it. You got to make sure it's hooked up right. I've seen this on the general exam before too, and I know you general people are banging your head against the wall because my gosh, why would they give me this question when I probably don't even work on security and I'm not getting a security license? I don't know that answer, but I do know it's in the telecommunications distribution method manual book, and that's where the diagram is. And one of the things they do is they suggest that you could get the telecommunication book for the general exam, which I don't recommend that because it's an expensive book. But they actually list that on their references that general people could use this book too. So they must pull some questions from there. But it hasn't been a problem in the past. Everybody's been passing in the general, so I don't think you're going to have an issue there. But still, you need to know this. That could pop up and be an issue for you. Okay, so Americans with Disability Act. Want to talk to you real quickly about this. I've got to move forward here and try to get through this stuff as quick as possible. In Georgia, we follow the ADA guidelines, and they supersede NFPA and any other code requirements if it's in a public location, meaning that it can be accessible by wheelchairs or people that are disabled. Okay. And briefly, I've given you this sheet here and some ADA guidelines. You should read through those. Some of these have been on the exam before. This one here, you can't, if you look at this, the height requirement here, minimum height requirement for the forward reach of a wheelchair is 48 inches. So NFPA has a guideline in there, I think it's 52 inches maximum height on a pull station. But the ADA supersedes that. Now, as long as it's telling you, it's asking you about ADA, and it doesn't say NFPA 72 in it. And I'm going to explain that when we talk about the fire alarm booklets and stuff. We go over the fire alarm books. Minimum floor height is 15 inches. So I mean, any of your receptacles, any of your telecommunication outlets, things of that nature that you put on the floor in a commercial building, they have to be at least 15 inches off the floor. That's where the plug goes into the jack itself. Okay, not the housing or not the plate. It's the actual lowest plug point. Because in a wheelchair, it's difficult to reach any lower than 15 inches to unplug and plug things in. And it's more difficult to reach above 48 inches. So those are the restrictions there. And again, you're required to follow ADA guidelines, and this has been on the exam before. And you need to know those things. And you need to know these things as well here too. And I'll talk more specifically about that when we go over the fire alarm books, if you're unrestricted or if you're taking the alarm category. Okay? So again, 15 inches, 48 inches here. Now, you don't have this regulation, but you're in Georgia. You're responsible for knowing guidelines regardless of whether or not they've given you material on those guidelines. You're going to be a professional contractor, so you should know this stuff. So I'm giving you this information so that I make sure you do know it, okay? All right, I'm going to wrap it up here for now, and then I'm going to pick this up with going over the National Electric Code. Specifically, I want to review certain sections of the NEC code. I know yesterday or whenever we put in